This bomb weighs 30,000 pounds. Only one plane can carry it, and it was built for a single reason. In March 2003, American air crews unleashed the most advanced bunker-busting bombs in their arsenal over Iraq. Precision-guided GBU-28 and BLU-109 bombs, each built to smash through concrete and steel, were aimed at command bunkers and underground weapons stores across Baghdad and Tikrit. But when the smoke cleared, after-action teams found a pattern that could not be ignored. Satellite images and on-the-ground inspections revealed bunkers still standing, their reinforced chambers unbreached. Craters marked the surface, but inside, heavy blast doors and thick concrete walls had absorbed the shock. Some facilities showed only cracked ceilings or collapsed entrance tunnels, leaving their critical functions untouched. Field commanders forwarded urgent reports to the Pentagon. The existing munitions, despite their reputation, were failing to reach the deepest, most fortified targets. Intelligence officers warned that adversaries could hide weapons programs and command centers in these untouched sanctuaries. The Department of Defense issued a classified review. The United States lacked a weapon that could guarantee destruction of deeply buried, hardened sites. In the months that followed, the search for a solution would drive a new mandate, one that demanded a bomb bigger, harder, and more precise than anything built before. Boeing's engineering team confronted the challenge with sheer physical scale. The GBU-57 Massive Ordnance Penetrator stretches over 20 feet in length and weighs in at 30,000 pounds, nearly the mass of a city bus, all focused into a single narrow cylinder. Its outer shell is forged from Eglin steel, a proprietary alloy developed for maximum hardness, able to withstand the crushing forces of high-speed impact with rock and concrete. Inside, the bomb carries approximately 5,300 pounds of PBX 9502, a high-energy explosive filling that forms nearly a fifth of its total weight. Guidance is handled by a dual system, GPS, paired with a hardened inertial navigation suite, allowing the weapon to steer itself with meter-level accuracy, even if satellite signals are jammed or lost in the final dive. The bomb's smart fuse, buried deep within its core, is programmed to detect subtle changes in resistance as it tunnels downward, waiting for the precise moment to detonate, only after confirming it has reached the heart of its target. Every detail, from the bomb's elongated shape to its reinforced casing, is tuned for one outcome: to drive deeper than any previous weapon, and hold at risk the kind of underground stronghold that had once seemed untouchable. Yet, for all its mass and engineering, a single constraint would dictate how, and even if, this weapon could ever be delivered to its intended target. Only one aircraft in the world can carry the GBU-57, the B-2 Spirit. This stealth bomber's internal weapons bays were designed with exacting dimensions, each bay measuring just over 5 meters long and less than a meter high, barely enough space to cradle the massive 30,000-pound penetrator. The B-2's airframe, a flying wing of composite materials and radar-absorbent coatings, keeps its radar cross-section vanishingly small, allowing it to slip past advanced air defenses undetected. But this pairing comes with trade-offs. To load 2 of the GBU-57s, every other munition must be left behind, and the aircraft's fuel is reduced to stay within strict takeoff limits. With a maximum range of roughly 6,000 nautical miles before aerial refueling, every sortie becomes a complex calculation of distance, payload, and risk. The entire mission, striking a single deeply buried target, depends on a handful of bombers, each carrying just 2 weapons. If one B-2 is grounded or detected, the odds of reaching the target drop sharply. The bomb's size and weight, dictated by the physics of deep penetration, tie its fate to the rarest aircraft in the U.S. arsenal. This constraint hangs over every operational plan, raising a question that no engineering breakthrough can fully resolve. Can a weapon be truly decisive if its delivery depends on a fleet counted on one hand? In 2009, a Defense Threat Reduction Agency analyst pored over fresh satellite images from the Alborz Mountains near Qom, Iran. The images revealed a facility carved deep into the limestone, a complex later identified as the Fordow Uranium Enrichment Plant. Intelligence estimates placed the main centrifuge halls beneath 80 to 90 meters of rock, shielded by reinforced concrete and steel. For United States planners, this was a new kind of problem. No existing weapon could guarantee destruction at such depth. Fordow's design was deliberate, a network of tunnels and chambers hidden from view and protected by a mountain. Layers of weathered limestone gave way to denser strata, with sections of basalt forming a natural barrier. Each meter of overburden added another obstacle, both to detection and to any hope of a successful strike. General Dan Kane, then a senior advisor on hard target planning, became the Pentagon's point man for the Fordow dilemma. In closed-door briefings, he described how the facility's depth set the benchmark for the entire United States bunker buster program. The question was no longer whether the United States could reach a buried target, but whether it could reach this target, one designed to survive everything short of a direct nuclear hit. DTRA's own technical assessments concluded that Fordow's 80 to 90 meters of layered limestone and basalt would defeat every penetrator in the arsenal at the time. The overburden was not just a geological detail, it was a strategic shield, calculated to stay just beyond the reach of conventional munitions. Every technical requirement for the Massive Ordnance Penetrator — weight, length, casing hardness, explosive yield — traced back to this single mountain. The bomb's designers faced a simple but unforgiving equation: defeat Fordow or accept that some targets would remain untouchable. As the Pentagon's focus narrowed to this benchmark, the next phase would test whether engineering could overcome the limits set by the Earth itself. Engineers at White Sands Missile Range began full-scale drop tests of the GBU-57 in 2008, using instrumented blocks of limestone and reinforced concrete to simulate buried targets. Each test was a high-stakes exercise in physics and precision. The bomb, weighing 30,000 pounds, accelerated to impact velocities between 350 and 420 meters per second. Upon striking the target, sensors embedded in the casing and nose relayed data on shock, deceleration, and trajectory. The goal was not just to break rock, but to prove that the weapon could survive the crushing forces of impact, maintain a straight path, and delay detonation until it reached a void, mimicking the heart of a hidden facility. Early results showed average penetration depths of 58 meters in homogeneous limestone, with the deepest test reaching 62 meters under ideal conditions. The smart fuse, designed by Boeing's Sensor Systems Group, became the silent arbiter of success. It combined micro-accelerometers with a capacitive sensor, reading subtle changes in resistance as the bomb tunneled downward. When the fuse detected a sudden drop in density, a signal of passing from solid rock into an empty chamber, it triggered detonation with a margin of error under half a second. This void detection feature was validated in the field, marking a leap forward from the time delay fuses of earlier bunker busters. Behind each test stood teams of engineers and maintainers. At White Sands, crews reassembled casings, swapped out damaged noses, and recalibrated sensors between drops. Meanwhile, at Whiteman Air Force Base, the 442nd Missile Maintenance Squadron established climate-controlled vaults to house the growing stockpile. By 2012, the first batch of operational GBU-57 weapons, about 30 units, was transferred to these vaults, where each bomb underwent annual inspection and electronic health checks. Over the next decade, at least 7 distinct variants entered service or test rotation. Some carried enhanced blast fills, others featured modular warheads, and a few were equipped with extra instrumentation for data collection. The evolution was relentless, driven by lessons from every drop and every maintenance cycle. Yet for all the refinement, a single question lingered over the program. Had the engineers truly solved the problem of reaching the deepest, most protected targets, or had they only come close, still at the mercy of the unforgiving physics that defined each test? Independent physicists and engineers began running their own calculations, separate from the Pentagon's official claims. Using finite element modeling and empirical formulas, they tested what a 30,000-pound steel penetrator could actually do against real rock. The numbers told a stark story. Even under perfect conditions, vertical impact, no loss of velocity, homogeneous limestone, the models predicted a maximum penetration of about 8 meters. Not 60, not 80, but 8. Introducing real-world factors, such as fractures in the rock, slight deviations in impact angle, or energy loss to casing deformation, pushed that figure even lower. Peer-reviewed studies and engineering blogs converged on the same range, casting doubt on the weapon's ability to threaten the deepest targets. For every meter gained in laboratory simulations, the complexity of actual geology took another away. The promise of unstoppable force met the limits of earth and stone, and the 8-meter reality became a quiet but persistent challenge to everything the program set out to achieve. In early 2024, the Air Force Acquisition Office ordered a rapid expansion of the GBU-57 program, authorizing a jump from 20 to 60 bombs per year. Congressional budget lines allocated $1.9 billion to the effort, citing rising threats from hardened sites in Iran and North Korea. At Wright-Patterson, Air Force Research Laboratory scientists outlined plans for the next-generation penetrator, a weapon designed to reach at least 95 meters into rock, exceeding the best test results of the GBU-57. The new penetrator will rely on advanced alloys and rocket-assisted impact, aiming to overcome the geological barriers that have stalled progress for years. Meanwhile, engineers at Northrop Grumman finalized designs for the B-21 Raider, the only bomber slated to carry both the GBU-57 and its successor. Program managers describe a relentless cycle as adversaries dig deeper, production lines accelerate, and the race for deeper penetration continues. The arms race beneath the surface is far from over. Today, the physics of rock and steel still dictate the limits of power. As nations deepen their defenses and weapons evolve in secret, each breakthrough shifts the line but never erases it. In this arms race beneath the surface, certainty remains as elusive as the targets themselves.